So I want to introduce these, well, two notions really. One of them is the notion that if we want to understand how the brain computes and processes information, we need to look at population activity. We need to look at the collective activity of large ensembles of neurons. And the second concept that I hope you take home after my talk is that although this population activity defines trajectories, defines the dynamics that occurs in a very high dimensional neural space, because there are millions of neurons that are modulated every time you execute a simple task, like I reach for my tea and I bring it close to myself. And there is at least 1 million neurons in motor cortex that are being modulated when the task takes place. But in spite of the fact that the activity takes place, that the relevant activity takes place in a very high dimensional neural space, this activity is mostly confined to low dimensional structures within this very high dimensional space. And these low dimensional structures are the manifolds that I will be telling you about. So I will use a very simple motor task to illustrate and motivate the ideas, and then I'll tell you about neural manifolds explicitly in this context of control of movement, because it's a motor task, but I'll also make some comments about the fact that these manifolds are much more general and ubiquitous than just in motor cortex. And then, because it's a theory seminar, I want to put forward a philosophy that I always try to convey very clearly to my students, which is that although the systems that we're studying are nonlinear, we should always study with a linear approach. We should always start by applying linear methods, see how far we can push them, see where they fail, and then that gives us some intuition of how to go nonlinear. You know, the world of nonlinear, the universe of nonlinear models and methods is so vast that it's very hard to go into that territory without some guidance. And I argue that the way in which the linear methods fail give us guidance for that. On the other hand, linear methods sometimes are unreasonably effective, and that's the example that I'm going to show you has to do with the unreasonable effectiveness of linear methods. I want to start by telling you about the collaboration that put forward the work that I'll be using in the last part of my talk. I have a long-standing collaboration with Lee Miller, who runs a monkey lab at Northwestern University. So we have co-supervised many students and many postdocs together. Their experimental component and a theoretical component. Juan Gallego was a postdoc with us at the time this work was done. He's now an assistant professor at Imperial College London. Matthew Perich and Raid Chowdhury were graduate students. Raid is now a postdoc at Pitt with a group of Aaron Batista, and Matt is doing a postdoc with Canonical region in New York. So let's start with a simple motor task. Let's go for the science. So this is a monkey. You humans also do this task. I will show you data from humans. The task is called a center out task. You have a center target surrounded by 8 targets that are arranged in a circle around it. The task starts by fixating at the center. Then one of the targets is illuminated. And there is a wait period that is random and is controlled by the experimenter. The subject has to wait for a go cue. When the go cue comes in, then the subject initiates a reach to the target, that is the target of that particular trial, and stays there and gets a reward. So it's a center out task. It's delayed. It's with an instructed delay, and it is the monkeys are extremely trained on this task. They do it over long periods of time in very stereotypical manner. I'll show you more about it. So the story that I want to tell you starts in the early 80s, when the lab of Georgopoulos started doing single unit recordings in primary motor cortex. So this is just one electrode you record from a single neuron during the execution of the center out task. So here, each row corresponds to a different trial, not to a different neuron. It's always the same neuron. And you have trials in all possible 8 directions in which the targets are arranged. And as you can see, although there is a lot of variability in the neural activity. So if you look from raster to raster to raster, every trial is different. However, there is also a lot of specificity. Clearly, trials in which the target is to the left of the subject cause an increase in the firing rate of this particular neuron. Trials that go to the right cause a decrease, a suppression of firing rate. So there is a modulation of the firing activity of this particular neuron in primary motor cortex in M1 with the direction of the reach, with the direction of the target. So this led to a very novel idea at the time, which was the idea of a tuning curve, that was cosine shaped. So if you plot the mean firing rate during a period of about 300 milliseconds, which is the period of the reach, as a function of the direction of movement, that is to say you have 8 points in here, they argued, the Georgopoulos lab argued that this tuning curve could be written as a cosine tuning curve. So you have a preferred direction for that particular neuron, is the direction in which the firing rate is maximum. So you write the cosine of theta minus the preferred direction theta I for that neuron. The cosine goes between -1 and 1, so you add 1 to it, now it goes between 0 and 2. You take a half, so now it goes between 0 and 1. You modulate it with A sub I. A sub I is the amplitude of modulation from baseline to maximum firing rate for that particular neuron. It might be modulated by R, which R is the extent of the reach, although most experiments are performed at a fixed distance R from the center target to the outer targets. And then there is a baseline BI, which is the firing rate of this neuron in the opposite to the preferred direction. So there are 3 parameters here: baseline, amplitude of modulation, preferred direction. And these 3 parameters completely specify, according to this model of cosine tuning, completely specify the firing rate of the neuron. So nowadays we do more sophisticated experiments. We don't do 1 neuron at a time. The lab of Linear implants is multi-electrode arrays, which are 10 by 10 electrodes. So this is about 100 electrodes. It's 96 actually, because typically there are no electrodes in the corner. This is 4 millimeters wide, so there's 400 microns between adjacent electrodes. And the electrode gets implanted in primary motor cortex. The primary motor cortex goes like from ear to ear, essentially, in the arm area, in the contralateral arm area. So if the movements are being executed with the right arm, the electrode will be implanted in the left arm area of primary motor cortex. And this is the data that we get nowadays. So now each row doesn't represent a trial. This is all one trial. This trial is about 25 seconds. And as I'll show you in a minute, during this trial, 3 different reaches have been executed to 3 different targets. Now every row in this raster plot represents a different neuron. So in this particular raster that I'm showing you, there is about 80 neurons that were recorded and about 20 seconds of data. I'm showing you this slide because this is a very important historical importance. So this was taken by the group of John Donahue and Brown, and this is 110 neurons, says 110 neurons, M1, primary motor cortex, human subject 3. This is data from human subjects that were waiting for epileptic surgery. And while the dura was open, the electrode was implanted, and they executed the same central task that I just showed you. And it's very interesting how, I'll try to explain later, the analysis of this data leads to very, very similar conclusions than the analysis of the monkey data for this particular simple task. So how do we present the data? We present the data as a matrix. And in this matrix, every row represents one of the neurons that we are recording to, and every column represents a time. So time has been discretized. It's we create bins of size delta. So we start at t plus 1, t plus 2, all the way to t plus capital T. Capital T is the duration of the experiment, measuring these units of bin size delta. And we record of the order of 100 neurons. However, as I said in the case of the monkey, if we were to record all the neurons that participate in the task, we will have to be recording of the order of 10 to the 6 of a million neurons. So this is the ideal case. In the ideal case, we are recording what Harris calls n infinity, which is really not an infinity. an infinite number of neurons, but he has in mind recording all the neurons that you could possibly record from that are related, because activity is related to the execution of this particular task. So in the ideal case, if you could sample everybody, this matrix would have n infinity rows, the total number of neurons modulated by the task, and as many columns as the duration of the experiment in this discrete time that we are using. But in practice, of course, we subsample. We have this electron array, and we don't have n infinity neurons. We have n sub d neurons, where n sub d is the number of neurons that we're recording from. It's of the order of 100 for these multi-electron arrays. It's of the order of thousands for neuropixels, but still a significant degree of subsampling compared to the actual population of neurons that is co-participating in this task. So this capital D is what is called the ambient dimension. It's an empirical dimension. You're not sampling the full neural space. You're only sampling a d-dimensional proxy of the full neural space. So this is again the similar data to the one I showed you before. Oops, sorry, I don't know what happened. And again, taking with a multi-electrode array, every row represents a neuron. And this, as I showed you, as I told you earlier, is about 20 seconds of data. And there have been 3 reaches in this time, a reach to the yellow target, to the red target, to the target. The targets are color-coded according to the scheme. So we're going to take actually a very wide delta t, a delta t of 300 milliseconds, which involves the whole duration of the reach itself. And this is the name of the decoding game. The decoding game is as follows. If I tell you, for each one of these columns that I'm showing here, the number of spikes emitted by every one of the neurons, and I then divide by 300 milliseconds, so I give you the firing rate of every neuron during that time. Would you be able to tell me whether the target was, whether the reach was to the yellow target or the red target? So how can we possibly visualize this problem? Of course, we cannot visualize it in 80 dimensions. So I'm going to do a very crude attempt at a 3-dimensional visualization. I'm going to show you neuron 46, which is a neuron that fires a lot, neuron 70, which is a neuron that fires very little, and neuron 78, which is a neuron that fires in a kind of irregular manner, sometimes more, sometimes less. So I'm going to go to a 3-dimensional space where the axes are the firing rate of neuron 46, the firing rate of neuron 70, the firing rate of neuron 78. There is only 1 point per reach because I'm not following the trajectory. I'm just telling you the total activity over these 300 milliseconds for the reach. So every point has these 3 coordinates. Every reach is represented as a point in this 3-dimensional neural space. And after I'm done putting all the points in this 3-dimensional space, I color them according to target. As you can see, you cannot learn anything from this plot. You cannot learn what was the most likely target from the position of the point, simply because there is no clustering here. There is no organization. There is everything is intermingled. So clearly, this is not a very smart way of thinking of this 3-dimensional space. So we were scratching our heads and thinking what to do. And then we say, well, let's go back to basics. Let's go back to the idea of cosine tuning. Not that we fully support the idea of cosine tuning, but let's take that very simple point of view that every neuron is acting according to its own cosine tuning curve. So what would happen if we're recording from n neurons? Well, then the firing rate of the population can be written in this way. It's just 1 page of algebra to get that. We have a vector b, which is the vector of baselines for all n neurons. We have again the factor of 1/2 and r, which is the extent of the reach. A vector A, which is the vector of amplitudes of each one of the neurons, the amplitude of modulation, A1 to AN. And then we have a linear combination of cosine theta and sine theta, where theta is the direction of the reach. And the vectors that we are linearly combining with cosine theta and sine theta are phi x and phi y. The components of phi x are the amplitudes and the cosine of the preferred direction. And the components of phi y are the amplitudes and the sine of the preferred direction. So now if I go to the n-dimensional space, this is for n equals 100, and I vary theta in this equation, what I will see is a circle, a 2-dimensional arrangement, which is very well reflects the organization of the targets in space. And moreover, if I allow for a little bit of variation in R, in this case, R between 10 and 11, there will be a 3rd dimension coming in. So this told us, this suggested idea that we must look for this activity, not in the 3-dimensional space of a few neurons, but looking at the collective excitations of these this population that we're recording from, of the order of 100 neurons. And we were using principal component analysis and getting plots of this type and getting very, very excited about it. This is more than 10 years ago. And we were scooped. We were scooped by very good colleagues, actually, the group of Krishna Shenoy at Stanford, where they use this idea of three neural modes. And the rest of my talk is just devoted to telling you what these neural modes are. These three neural modes. And when you go through three-dimensional space spanned by these three neural modes, what you find is very nice clustering, but not only clustering, but the order in which these representations appear follows the order of the targets in real space. So you go from red to orange, from wine to red to orange to yellow to green, and you go from one to red to orange to yellow to green. So we are capturing something essential about the structure of this task, which is how are these targets organized in real space. But the representation is not a representation of individual neurons, it's a representation of neural modes. So what are these neural modes? These neural modes are, like we were using principal component analysis, are directions in neural space, are vectors that point in a given direction in this space of individual neurons, and they indicate a specific pattern of population activity. So if you have two neurons, N1 and N2, and the vector goes in the 3-1 direction, it means that every time neuron 1 fires a given amount, neuron 2 fires a given amount, neuron 1 is going to fire 3 times as much. And you could excite this mode more or less, but you are always on that line that indicates a particular relationship between the firing rate of these two neurons. So neural modes are directions in neural space, and they indicate specific patterns of population activity. So let me show you how this leads very naturally to the idea of low-dimensional manifolds for the control of movement. So this is a scheme of the experiment we are doing. We have a very large population of neurons participating in the task. We put in an electron array that allows us to simultaneously record from capital D neurons. This is the ambient dimension D, and in this case, we're recording neuron 1, neuron 2, neuron 3. We see the spikes. That's the raster. We see the spikes emitted by these three neurons as a function of time. So what happens if we now follow the activity of these neurons over time? So instead of taking a very large 300 millisecond beam, we take a smaller beam and we just follow the activity as a function of time. So at any time, we get a point in this three-dimensional neural space, N1, N2, N3. But when we follow these points as a function of time, we see that the trajectory doesn't fill the three-dimensional space, doesn't fill the full three-dimensional neural space, but it remains confined to a low-dimensional manifold, in this case, a two-dimensional hyperplane. So this is the idea of dimensionality reduction, and the idea that the population dynamics is actually constrained to a low-dimensional manifold within the very large empirical neural space, which is, of course, nothing but our poor attempt at capturing a very, very, very large actual neural space. So we are going from 10 to the 6 actual number of neurons modulated by the task to about 10 squared, about 100 that we can actually measure. And I will show you that of the order of 10 is sufficient to describe this manifold. Actually, for this very simple task, I showed you already that 3 is sufficient. A neural space spanned by only 3 neural modes suffices to capture the structure of the task. So this is then the idea that you have a high-dimensional neural space, but within this high-dimensional neural space, you have a neural manifold that is spanned by neural modes, and that the activity during the execution of the task, the trajectory described by the population activity during the execution of the task, is confined to that low-dimensional manifold. If the low-dimensional manifold is linear, it's a hyperplane embedded in the high-dimensional neural space, then life is easy because we have a basis, in this case, a two-dimensional basis, the vectors C1 and U2, that completely span the hyperplane and that allow us to fully describe the trajectory. But we have to allow, of course, for the possibility that the trajectory is confined to a manifold that is not linear, but is curved. And in that case, we have to be more careful about how we're going to describe that manifold. So the manifolds, as I say, can be linear and nonlinear, but even nonlinear manifolds can be embedded in low-dimensional neural space. on non-dimensional flat spaces. So for instance, here we have a manifold whose intrinsic dimension is 1, but it can be embedded in a flat space whose dimension is 2. However, if I start taking this little circle and pinching it in different directions, I will need 3 directions of 3 dimensions of a flat space in which to embed it. And actually, this little circle is really embedded in a 100-dimensional space, and I start pinching it in all possible directions. I might need all 100 dimensions of the flat space in order to describe these nonlinear manifolds. So nonlinear manifolds are complicated objects, and this point was very nicely made. We had a workshop at the Computational Neuroscience conference 2 years ago, and both Søren Osterjic and Ila Fitte made very nice points about this differentiation, this distinction between the intrinsic dimension of the nonlinear manifold. In this case, if you're living in the surface of the sphere, would be 2. But if you really want to look at your embedding dimension, which is the flat dimension, in which the smallest flat dimension in which can be embedded, then it's going to be 3. So, one last point I want to make about these low-dimensional manifolds is that once you're in the low-dimensional space, which really contains all the activity and is sufficient to explain the activity, we talk about latent variables. We talk about latent variables about the activation of these dimensions that are sufficient to explain the non-neural manifold. And the point that I want to make is that these latent variables are themselves generators of the actual spikes. So if you look again at these 2 vectors, U1 and U2, I can project the activity in the direction of U1. I call that time-dependent activity latent variable 1. I can project it in the direction of U2, that's latent activity 2. And now I can use the fact that these 2 vectors are directions in the full neural space. So this is actually a 3-dimensional vector. U2 is also a 3-dimensional vector, to project back the latent activity into the neural space. So I use in that case these basis vectors as columns. This is the vector, the 3 components of the vector U1, the 3 components of the vector U2, and from the latent variables I can reconstruct the neural activity. So in this sense, we really have adopted the point of view in our analysis of neural data that these low-dimensional manifolds and the corresponding latent variables are the building blocks of the population activity. And that the correct thing to do is not look at the time evolution of the firing rate of individual neurons, but look at the time evolution of these particular directions in neural space, the neural modes. How does the activity of every neural mode change with time, and follow those latent variables as the builders of description. So we wrote a little perspective paper, or sort of mini review paper in 2017 about this topic. And there we were focusing on the neural control of movement, and we talk about the neural modes as building blocks and the latent dynamics, which is the time-dependent activation of the neural modes as the building blocks to generate neural activity in primary motor cortex and therefore generate behavior. But we already pointed out in our paper that 4 years ago, so it's an old list, that the same neural modes and the same restriction of the population activity to low-dimensional manifolds has been seen in many other areas, in sensory areas like visual, auditory, and olfactory cortices, and also in areas like frontal, prefrontal, and parietal cortices. So it's not just a property of M1 or areas of the brain associated with the neural control of movement. It's a very genetic property. And since then, since 2017, there's been many more papers that have also adopted and used this point of view to make progress in our description of population activity. So let's go back to the theory part of it. Let's go down to the last part of my talk, which is the theory part. I want to show you how to use the important tools that come all really from linear algebra. I'm always surprised that over many years of professional activity, I keep on using linear algebra and I keep on learning new things, learning new tools that come from linear algebra. So this is the task that I showed you before. Let's go back to the central task that the monkey is executing. What I want to show you is the behavioral stability with which the monkeys perform this task. They are overtrained. So this is a monkey that has been coming back to the lab over more than 2 years. And every now and he does other things, every now and then he goes back to the central task. So these are the trajectories in the XY space, and again, color coded according to target. And you can see that the trajectories on day 1, day 462, day 730. So this is like a year later, 2 years later. The trajectories are very stereotyped. If you look at the trajectories on a given direction, this in case is up and to the right, to the northeast direction, and you look at the velocity profile, so the cursor is making a trajectory in the XY plane of the screen. So the X velocity has a trajectory, the Y velocity has a trajectory, X is darker, Y is lighter, and you can see that the time evolution of these trajectories is also very, very stereotyped. So you can look at the correlations of the hand velocity both along the X and the Y axis. The blobs correspond to the time where the activity was measured when the monkey was doing this particular task. And you can see that they are very, very close to 1. Actually, if we plot all the correlations in a single histogram of 630 different trials spanning these 2 years of activity, you can see that the behavior is very stereotyped. And this is not just unique to this task. You know, there are many tasks that we do in a very stereotyped manner. If you are, so for instance, I watch tennis sometimes, and Nadal has a very, very idiosyncratic and specific way of serving, and he always serves in the same manner. Actually, I think I could give you like a silhouette of him serving, and you will be able to tell that it was Nadal. So when you repeat, you keep on practicing and you repeat a movement many, many times, you acquire a stereotyped manner of doing it, and it's very reproducible in terms of the dynamics of the kinematics of the limb in space. So this is the behavioral data, and it shows a large degree of stability in this very well-learned task. So we would like, we made an hypothesis. We said, well, we think that this stable behavior is a reflection of a very stable population activity at the neural level. And we would like to test for that idea. The problem is that when we come back 2 years later, the electrode array is not measuring the same neurons. Some electrodes develop scar tissue around themselves, and we lose those neurons. The electrode goes down a little bit into the brain, and it picks up new neurons. So if you look at day 1, you are recording neuron 1, 2, 3. If you look at day n, you're recording neuron 4, 5, 6. There will be some degree of overlap, but many of the neurons that you're recording are not the same. So this was our hypothesis was okay, because the subjects are consistently performing the behavior over days, months, and even years. There has to be a latent activity associated with this consistent behavior, which is also consistent, which is also stable. But how are we going to check for that when we cannot record from the same neurons over a very long period? So we need to compensate from the fact that there is a true latent dynamics, there is a true manifold of the order of 10 to the 6 neurons, in which there is a true neural space of the order of 10 to the 6 neurons, in which there is a true manifold, which we claim is stable, but I am projecting that manifold into an empirical space on day 1 and a different empirical space on day n, where the empirical space is the space of the neurons that I'm recording from. So this is what we mean by this. So this is the very high dimensional true neural space in which there is a true neural manifold. I have no idea what this dimensionality might be. And there is a true dynamics, which I claim remains stable. On day 1, I'm measuring an empirical space, which is empirical neural space, which is defined by the neurons that I record on day 1. And the trajectory, the manifold gets projected into that, and the trajectory gets projected into that. Now, all these dimensionality reduction things that take place are all projections, and they are all linear operations. And the same thing happens on day n, where again, some of these neurons might or might not be the same as on day 1. So this empirical neural space on day n might have some overlap with empirical neural space on day 1, but in this empirical neural space, we again find a projection of the true neural manifold. We find a linear projection. We're going to do principal component analysis. We're going to stay very simple. And there is a trajectory. Now, these trajectories might look very different, but our idea was that there should be a linear method that allows us to align these different manifolds that are embedded in different empirical neural spaces in such a way that the trajectories themselves get aligned. And if you can do that, then we can show that there was an underlying trajectory in the true manifold, which remains stable. And so we can do that, and I'll walk you through the process that allows you to do that. So we start with the same data matrix as before. Every row corresponds to a neuron. Every column corresponds to a time. There is many trials embedded in this matrix, captured by this data matrix. And the number of neurons that we pick is we do a union of the set of neurons recorded in day n and the set of neurons recorded in day m, so that every possible neural axis is included in that space. When a neuron was recording in one day and not on the other one, we put zeros for the activity of that neuron in the corresponding data matrix. So we have a data matrix for day n and a data matrix for day m. They are all d by t, as I said, where d is the cardinality of the union set of the neurons recording on day n and day m. T is the duration of the experiment, and it captures many trials. And for each one of these two data matrices, we do a singular value decomposition, which gives us a basis U in neural space. This will be like the U vectors that we talked about earlier, and a basis V in the dynamic space along the time evolution of the system. So what we're going to do is do simply a principal component analysis. So we have our matrix U. Our matrix U is a D by D matrix, and they are ordered according to the eigenvalues of the singular value decomposition. So we are going to keep the lowercase d leading eigenvalues. So just that we are going to keep like U1 and U2, just a few columns. And these few columns will span a d-dimensional hyperplane on day n, and a different d-dimensional hyperplane on day n, because these matrices are different on day n and day m. And this restriction to lowercase d dimensions is the restriction that allows us to do the principal dimensionality, the principal component analysis of the linear dimensionality reduction, in which we go from the empirical manifolds to the empirical neural spaces to these low dimensional manifolds. So what we are doing is we have projected into the empirical neural space to get the matrix X, and now we're creating this even lower dimensional flat embedding manifold, a hyperplane essentially. So now we take all the data and we project it into that hyperplane. So we take the d-dimensional manifold spanned by the neural modes of the day n and day m, and we obtain the latent variables. So the latent variables are of dimension d by t, where d is the dimensionality of the flat manifold and t is the duration of the experiment. And we do that by taking the data matrix X and projecting it onto the leading rows, which were the leading columns, but here I'm using U tilde transpose, the leading columns of the corresponding U matrices. So I get a set of latent variables on day n and a set of latent variables on day m. And those are the ones that I want to align. So let me actually go directly to this. So before I align them, if I ask what are the correlations between the dynamics on the manifold at day n and the dynamics of the manifold at day m, when I can just simply project these latent variables onto each other. But what I want to do is align them. And so in order to align them, I'm going to use another linear method, which is canonical correlations. And canonical correlation starts with the QR decomposition. So we transpose the matrix L, so now they are very long vertical matrices. So every column corresponds to a different latent variable, and as I go down, it's a function of time. And we write these L's as Q times R, where the Q's are again D column vectors, and they provide an orthonormal basis for the column vectors of the corresponding matrix L transpose. And R is an upper triangular matrix. This is, for those of you who know physics or like physics, this is essentially like doing a Gram-Schmidt decomposition. So the first column of Q is going to be the first column of L rescaled. The second column of Q is going to be a linear combination of the first and second columns of L that is constructed to be perpendicular to the first column of Q and then normalized. And this is why R is an upper triangular matrix. So we can essentially create an orthonormal representation for these dynamics on day n and day m, but they are low dimensional. They are living in a space of the latent variables on these hyperplanes of dimension lowercase d that I constructed, each one of them living in its corresponding empirical neural space at these different days. So we construct now the same inner product instead of LL with a QQ. And remember that Q is like L transpose. So this is why L transpose is like Q transpose Q. We do this inner product and we do a singular value decomposition. This singular value decomposition will give me a new basis for day n and a new basis for day m. These are bases within the latent spaces. And the elements of the diagonal matrix are going to be the canonical correlations, and they are again usually sorted from largest to smaller. And they quantify the similarity in the aligned dynamics. So now what we have is we have these new manifold directions that maximize the pairwise correlation between latent dynamics across the 2 days. And because we have U for day n and V for day m, we can create new matrices that affect these correlations by again scrambling them in the way that had been unscrambled by using the matrix R. So the U's and the V's are orthonormal representations. The R's are triangular matrices that are going to mix them up. So the N and M are linear transformations, but they can be skewed axes. They are axes that have been scaled differently in different directions. And we use the M matrices to recompute the latent variables. And this is beautifully explained in a paper by Bach and Jordan, where this is where I learned about it. I recommend it strongly. So once we do that, we can align the stable dynamics. And this is where I want to show you how well we align. So this monkey, CR, is the monkey for which I had shown you data. This monkey is the monkey for which you have data for over 2 years. So if you come on one day and you measure activity early in the session and later in the session, the activities are very strongly correlated. They give you a baseline, which is the gray curves. But if you measure activity on day 1 and then on day 450, these activities are not very well correlated. The correlation coefficient has dropped from 0.8 to about 0.35 on average. But if you do the alignment that I told you about, then you essentially recover the correlations that we had seen earlier on. And this is the same thing for another monkey for which we have data for 45 days, a monkey for which we have data for 70 days, and a monkey for which we have data for over 2 years. And I really want to brag about this because, you know, when you do electrophysiology, you struggle to have data from 2 monkeys. And here we have supporting data from 4 monkeys over very different periods of time. So it's really an achievement. And I want to show you one more thing before I finish, which is usually what we are interested in is using this neural activity in the context of brain-machine interfaces. So I measure the M1 activity using these multi-electrode arrays, and I want to create a very simple linear decoder that allows me to then guide the cursor, so that the cursor is being guided by the neural activity as opposed to being guided by the hand moving the manipulandum. And I want to show you again that if we align, of course, the decoder, if you create a decoder with data on day 1, the performance of the decoder becomes abysmal as time progresses. So the gray is again the decoder trained at the beginning of the session and used during that session. The green is the deterioration of a decoder trained on day 1 if you insist on using the same decoder. And this is because you are capturing now a completely different or a mostly different empirical neural space that is providing input to the decoder as time goes on. And then if you first do the alignment that we talk about and then keep on using the decoder on day 1, it's the same as training a decoder every day. And this is very, very important for brain-machine interfaces, because if I retrain the decoder every morning when you come into the lab, it's like every day you have to learn how to ride a slightly different bicycle or how to drive a slightly different car, because I have changed the interface that connects your activity, in this case, your neural activity, to what happens in the outside world. It's much easier for the user to learn a decoder and keep on using the same decoder. But typically, this leads to a substantial deterioration of activity, which now we can avoid by realigning your neural activity of today with what's your neural activity on the one, which is the data, the statistics of the data that I use to train the decoder. So if I can perform the alignment, then everything works very nicely. So this is the basic idea that I wanted to convey to you, that there is a very large neural space that is associated with this task. And in that very large neural space, the dynamics, the trajectories that the system, the ordered way in which the system visits states as a task is executed is constrained to a low dimensional manifold, which could be linear or nonlinear. So there is a true dynamics and a true dimensional manifold. And in this method that we use to create, to try to measure the neural activity, which is these empirical neural spaces in which we measure of the order of 100 or 1,000 neurons, we are projecting the true neural activity onto these empirical neural spaces that are lower dimensional. And in these empirical neural spaces, we again try to find the latent manifold, the neural manifold to which the activity is constrained. And in this case, we have used sort of simple linear methods to find that manifold. So that manifold is actually a hyperplane on which we project the dynamics, the empirical dynamics that we measure. We project the activity of all the neurons that we measure. And we can do it in different ways. And then we can use different, we can use canonical correlation analysis, which is again a linear technique to align those dynamics. And we have a paper that came out last year after a long and protracted argument with referees, which essentially wanted us to go back to the Georgopoulos idea and show that all this could be shown by invoking so again, if you're a physicist, this would be like an ideal gas of neurons that don't talk to each other, but each one of them has its own tuning curve, its own cosine tuning curve, and everything could be explained on the basis of individual cosine tuning curves without invoking any kind of neuron to neuron interaction. We argue differently. We argue that the population activity is the actual relevant quantity, and the population activity indicates strong covariance between the activity of different neurons. This is why the population activity is constrained to low dimensional spaces and to low dimensional manifolds, be it subspaces or be it curved manifolds. And that this covariation is nothing but a consequence of the fact that this network of neurons is connected. Neurons covary because they either receive common input or because they are connected. And it's the connectivity of the neurons in a network that gives rise to these low dimensional manifolds to which neural activity is constrained. Actually, there is a beautiful recent paper coming from the lab of Sara Ostojic, in which he shows that if you connect to a recurrent neural network at random, then the rank of that matrix is equal to the full number of neurons in the network, and the activity, the dynamics of the network is not constrained to a low dimensional manifold. But then he trains the network to perform a task. Actually, he trains the network to predict the muscle activity during the center out task. So it's again the center out task with 8 targets, but in a muscle language. And then he shows that not the original network, but the learned network, the learned connectivity of the network is now a connectivity matrix of smaller rank, doesn't have full rank n, has lower rank. And therefore the dynamics of that network can only explore a low dimensional structure within the high dimensional space. So again, that is a flat manifold within which there might be a non-flat manifold of even lower dimensionality that is embedded. But even by studying the flat manifolds, we can learn much about the task. And so there is a lot of work being done along the lines of these concepts, and I'm showing you here some more recent references. We need to understand how these manifolds are created during learning, and they are maintained by practicing, then we ask ourselves, as I said, whether this intrinsic dynamics that is restricted to low-dimensional space is actually the dimensionality reduction associated with this intrinsic dynamics is determined by the connectivity. So is the geometry of this low-dimensional manifold determined by the connectivity? And then, of course, the dynamics in the brain, they are never purely intrinsic. They are every area of the brain is constantly being bombarded by inputs. And then the question that we ask is, what is the role of these input-driven dynamics? Do they affect the dimensionality and the geometry of the manifold? Or it's just that there is a manifold associated with each task, and the input dynamics is just the drive provided by the inputs is just used for switching among different manifolds. So in this view of low-dimensional neural dynamics acquired by learning and that they are task-specific, we can, sort of be pretty relaxed about problems of capacity because we have this very high-dimensional neural space, enormously high-dimensional, and within it we have these low-dimensional manifolds that could be flat, could be curvy, could be very curvy, and they are not even fully explored. It's not that you fully explore the hyperplane, you explore a region within that manifold. So there is very little chance, and some calculations are going on and as we speak, and that's again another open area. There is very little chance of hitting a capacity limit in terms of how many different tasks could you learn and how many tasks could you embed in M1, for instance, how many different motor tasks can you learn. And that's the way where I want to finish again by reminding you that this the part of the work that we have contributed to is done in collaboration with Lee Miller, Juan Gallego, Matt Berridge, and Rahid Chudhuri. And that's it. Thank you so much.